Welcome to MrAITech. If you love technology, AI, and the innovations shaping our future, hit the subscribe button and join our community. New exciting content is coming soon, so don't miss out. Thank you for watching and enjoy the video.
Welcome to This Explainer. We are literally right in the middle of a massive, unprecedented global shift toward electric mobility and electrified industry. And, at the heart of this entire revolution is a piece of technology that's incredibly powerful, yet surprisingly simple. It's the electric motor. Today, we're going to break down exactly how this technology actually works, why it's fundamentally changing the way we move, and the massive industrial realities of keeping all these motors spinning. Let's get into it.
Okay, let's dive right into our roadmap for today. We'll kick things off with the electric engine revolution, zoom into the anatomy of electric motion, and then look at the motors powering modern EVs. After that, we'll uncover the hidden cost of failure and wrap up with how we keep the world running.
Section 1. The electric engine revolution. Why the world is moving away from combustion.
Think about it. For over a century, we've basically relied on tiny, controlled explosions to move our vehicles around. It's a technology that's definitely served us well, but man, it comes with some severe mechanical limitations. A traditional gasoline engine relies on hundreds of complex moving parts. We're talking pistons, timing chains, valves, spark plugs, the whole shebang. All of these parts rubbing together create immense friction and heat. Because of that, a gas engine only really achieves about 20 to 35% efficiency. Most of the energy from your fuel is literally just lost as heat. An electric motor, on the other hand, it operates on a completely different paradigm. It has absolutely minimal moving parts, mostly just the stator, the rotor, and the inverter. Because it relies on magnetic fields instead of actual combustion, an electric motor easily blows past 90% efficiency. Its simplicity is truly its greatest strength.
Moving on to Section 2. Anatomy of electric motion. Zooming in on the core of electromagnetism.
Now, at the microscopic level, the foundation of all this motion is just basic physics. Opposite magnetic poles attract, and identical poles repel. That's it. That is the fundamental law generating the torque. So the first major component that harnesses this physics is called the stator. You can think of the stator as the stationary outer shell of the motor. Inside the shell, there are these carefully arranged coils of wire. When electricity from the battery flows through these coils, it creates an electromagnet. And by actively controlling that flow of electricity, the motor generates a magnetic field that actually rotates around the inside of that stationary shell. This right here is where the electrical magic is generated.
So, the absolutely crucial point here is how we actually capture that rotating magnetic field. And that brings us to the rotor. The rotor sits right inside the stator, and this is the part that actually spins. As the magnetic fields in the stationary stator rotate, the magnetic poles of the rotor are continuously pulled along with them. It is endlessly chasing the magnetic fields generated by the stator. And in doing so, it takes that raw electrical energy and turns it into direct mechanical rotation that can be sent straight to the wheels.
A really great way to visualize this is the classic rabbit chasing the carrot metaphor. It's basically the ultimate unwinnable race. The rotor is our rabbit and the magnetic field is the carrot. But to keep the rabbit running, something has to perfectly time the movement of that carrot, right? Well, that is the inverter. The inverter acts as the motor's brain. It converts the direct current from the battery into alternating current constantly and dynamically, shifting the electricity in those stator coils. It moves the magnetic field forward just fast enough so the rotor never actually catches it, and therefore never stops spinning. This precise control is exactly why electric vehicles give you that instant, incredibly smooth torque the literal second you press the pedal.
Which brings us to Section 3, Motors Powering Modern EVs, applying the physics to the road.
Depending on what a specific vehicle needs, engineers actually use a few distinct motor topologies. For instance, you've got PMBL-DC, or permanent magnet brushless DC motors. These are highly efficient, hitting up to 98%, and they're totally maintenance-free, often used in lighter hub motors. Then you have robust induction motors. These are famously used in the Tesla Model S, and they're incredibly durable because, well, they don't use expensive permanent magnets at all. On the flip side, cars like the Chevrolet Bolt and the Nissan Leaf use PMSM, or permanent magnet synchronous motors, which are prioritized for their really high power density and compact size. And finally, we're seeing a rise in PMAI-SRM motors. These cleverly balance reluctance torque with a minimal use of rare earth magnets, which helps extend vehicle range while keeping the cost down. Basically, every single design is a precise trade-off between power density, cost, and efficiency.
And this brilliantly illustrates the level of precision involved here. What you're seeing is a finite element analysis of an advanced PM-BLDC motor, showing exactly how engineers push these materials to their absolute limits. Those intense red zones reveal a peak instantaneous magnetic flux density of 2.14 Tesla running throughout the tooth of the motor. Engineers rely on these highly complex simulations to push electromagnetic boundaries, ensuring that absolutely every single ounce of electrical energy is converted into forward momentum with minimal waste, no energy left behind.
All right, moving into Section 4, the hidden cost of failure, the massive industrial stakes of motor maintenance.
Zooming out from passenger cars to massive industrial manufacturing, it's actually these exact same electric motor principles keeping the globe running. But when they fail at this scale, the stakes are incredibly high. Take a look at this number, $210,000. That is the shocking average cost of just a single unplanned motor failure in a manufacturing environment. And that hefty figure combines emergency replacement parts, expedited shipping, and most importantly, the massive financial hit of lost production downtime.
But honestly, here is a fact that's even more staggering: 82%. A massive 82% of those catastrophic, highly expensive motor failures are completely preventable with basic, structured maintenance. The problem isn't the technology itself, Industrial motors are built like tanks. They're designed to last 15 to 20 years. The real problem is a lack of systematic care, which ends up dropping their average lifespan down to just 8 to 12 years.
So you might be wondering, what exactly is killing these motors? Well, the top causes of premature failure are entirely mechanical, not electrical design flaws. Bearing failures lead the pack by a wide margin, causing 68% of failures. Winding insulation degradation accounts for 58%, and shaft misalignment causes about 54%. What this really tells us is that simple mechanical neglect is the true enemy of the electrified world. Finally, Section 5, keeping the world running, world-class reliability and maintenance. Since bearing failures are the single biggest threat here, proper lubrication is absolutely vital. But it's not as simple as just grabbing a grease gun and adding grease whenever. World-class maintenance requires strict steps. First, you have to clean the fitting to prevent any contamination. Second, run the motor up to its operating temperature. Actually, you should never lubricate a cold bearing. Third, apply a precisely calculated amount of grease while the motor is still running. And fourth, operate it for 30 minutes to purge any excess grease. I really want to emphasize that last point because it sounds so counterintuitive, but over-lubrication alone causes 35% of bearing failures by creating excessive heat and pressure inside the housing.
To avoid these completely preventable failures, maintenance absolutely has to be driven by hard data, not just arbitrary calendar dates. And this brings us to the golden rule of runtime for bearing lubrication. You calculate the interval by taking 14 million and dividing it by the motor's RPM. So to put that into perspective, an 1800 RPM motor needs lubrication precisely every 7,800 operating hours. Guessing based on, just months on a calendar, that is exactly how those $210,000 failures happen.
Finally, we have to talk a bit about the control systems. These variable frequency drives, or VFDs, are essentially the industrial versions of those EV inverters we talked about earlier. Remember the whole rabbit and the carrot thing? Well, while VFDs are amazing for efficiency, they also create a new invisible threat. They generate extremely rapid voltage spikes and high-frequency harmonics. Over time, these rapid spikes severely degrade the motor's winding insulation and can even shoot electrical currents straight through the physical bearings themselves. Managing this demands rigorous, scheduled insulation resistance testing to catch any degradation before the motor completely shorts out.
So, as we wrap up this explainer, I want to leave you with this provocative question to ponder. As we rapidly transition our cars, our factories, and our massive energy grids away from combustion, are our global infrastructure and industrial maintenance protocols truly ready to support a fully electric future? The physics are elegant, for sure, and the technology is clearly superior. But the massive operational shift required to maintain it all, that is just beginning. Thank you so much for joining me today. Keep exploring, stay focused, and I'll catch you in the next explainer.